Hi gang, welcome back. What are we doing today? Mechanics of materials, beam bending. What do we got going on? We've got a beam that's loaded up here, and we want to find the absolute, that word is important, absolute largest bending stress in the given beam, okay? So how do we find the biggest bending stress in this beam? Well, you know what we need to do? We need to do this little shear moment diagram, don't we? We need to find out where the largest bending moment is, and then we can maybe calculate what the biggest bending stress due to bending is, okay? Now, how can I have normal stress of the beam? I can either have normal stress from what? Compression or tension, right? Or I can have normal stress due to bending, right? So that's going to be P over A stress is going to be the compression or the tension. And then MC over I, remember that equation. Okay, those are the two that we need to use. Okay, is P over A equals normal stress, or normal stress equals MC over I. Here's the cross section of the beam. Okay, so it's a nice little rectangular beam, isn't it? Here's the neutral axis. Boy, that makes my life easy, doesn't it? So we can calculate I real fast. I is, it's rectangle, 1/12. The base, 3, times, remember the equation? BH cubed, right? Height is 6 cubed. These are going to be in inches cubed, right? So equals, calculator. Here we go, calculator. 3 times 6 cubed equals divided by 12 equals 54. Okay? It's 54 what? Inches cubed, okay? That's that guy right there, okay? Now, here's a question for you. Just looking at this problem here, okay? Now, we're going to do some other things here. Like we got to calculate what is M. Is there any P over A stress in this problem? Is there any point of this beam that experiences compression or tension due to a force? Since all the forces are straight down, the answer is no. If that 14 was at an angle, right, then this section of the beam here would be in tension, okay? This section would be just along for the ride, but it's not at an angle. So on this problem, this particular problem, this guy right here, we're not going to have any of that. So always be sure and check that, right? Because those two things could add together, okay? So on this problem, we're only talking about MC over I stress due to beam bending, okay? We also know this, don't we? The bending at the neutral axis, the stress is going to be what? 0, right? There's no stress there. Why is there no stress? Because of C. What is C? C is the distance, okay, from the neutral axis to the point of interest. So that might be C down here on the bottom, right? There's one. Or, you know what? Since this is the same distance, that could be C up here on the top. Now, what's the difference in those 2 points? Okay. Well, as this beam bends, okay, like so, what do we know about the bottom of that beam? The bottom is going to be in what? In tension, isn't it? And tension is what? Positive, okay? The top is going to be in compression, so that's going to be a negative stress. So it's going to have positive stress down here. It's going to have negative stress up there. Do you understand that? Now, does that really matter? Not when you use the word absolute, does it? Because absolute means I don't care what the sign is, give me the biggest value, right? Whether it's tension or compression. Okay? So in this case, C for our problem here, because if it's 0 here, where's it going to be worst case, right? Boom. At the farthest I can get away from the neutral axis, which is going to be 3. Either this 3 or that 3, it doesn't matter. So C is going to be 3 inches. So the last thing that leaves me with is what the heck is this guy right here? Remember, M stands for bending moment, okay? And that's going to come from this load scenario here. And let's just do this, shall we? Whoop. What am I doing here? looks to me, let's see, V and M. We're doing a shear moment diagram, doesn't it? Okay, let's put some discontinuities everywhere something interesting is going to happen. Okay, something happens there. And let's see, V is going to be in what? V is in kips. Oh, my European viewers love them some freedom units from America. Okay, sorry y'all. And M, what is M? That's going to be in what? Foot kips. Okay, foot kips. All right. Now all this I got to be careful, don't I? Because this is in feet. What was that in over there? Yeah, I see some possibility of a mixed unit over there, don't y'all? All right, let's see if we can do this. Can we do it? All right, here's what we're going to do. Let's first convert that distributed load into a concentrated load. Let's see here. That's a this. Okay. And it's 2 kips per feet times, that's a 0 right there, y'all. Someone's been messing on my board. 2.0 feet. Okay. 2 feet. If I have 2 feet of it, that's 4, isn't it? 4 kips. Okay. 4 kips. All right, so if that's 4 kips, this is 14 kips, then I've got 2 reactions over here. I've got a normal reaction over here. We'll just call this BY, and we'll call this guy AY, shall we? Okay. I need to find those 2 reactions. How can I do it? Is it hard? Piece of cake, right? Sum of the moments at point A equals 0. Here we go. The 14 rotates me what? Remember, this is positive. That looks like negative, doesn't it? Minus 14 times how far away? 4.5. Okay. And then I've got that 4 over there, which also rotates me negative. So minus 4 times how far away? 4.5, 6.5. And then what do I do about this 2 feet over here? What do I do about that? What do I do about 2 feet? It's in the middle, isn't it? Okay, so 4, 6.5, and then one more is 7.5. Okay, and then finally the BY, which rotates me positive. So plus BY times how far away is that? 4.5 plus 4 more, 8.5. Okie dokie. Let's get our calculator out here. Oh, it's in my pocket. In my pocket. Hello, Poppet. Okay, so I have 14 times 4.5 plus 4 times 7.5. Move that to the other side. Whoop, equals 93. Divide that by 8.5. And that gives me 10.94. So BY equals 10.94. And that's kips. Okay. Remember, up stuff equals the down stuff, right? That's Spanish for the sum of the forces in the Y. So that means AY must equal what? What do I got going down? 14 plus 4. 18. That's right. So 18 minus that. 18 minus answer equals 7.05 left, right? 06. Okay, and that's what I have there. So here I have 10.94 kips, and here I have 7.06 kips. And there's our global equilibrium, right? Remember, if you foul up global equilibrium, you won't get back to 0 over here, okay? So if you do these problems and you don't get back to 0, your first thing you ought to be doing, 99% of the time, you screwed up global equilibrium. Dadgummit. But the bad news is you got to start the problem completely over again. That's the bummer, okay? So here we go. What do we want to do? Let's see. This is from statics. We know how to do this, don't we? Okay? That was statics. Here we go. We start off at 0. What do we have first? AY, right? We got our load backpack on. We get on the beam. We start walking. First thing we get, Van Halen force. Might as well jump. Okay, jump. Here we go. 7.06. Okay, then what? Look here. No change. No change, no change, no change. Bam! What happens right there? Somebody just put 14 in my backpack. Oh, well, I was at 7.05. Someone go minus 14 equals minus 6.94. Whoop. There we are. Minus 6.94. Okay, let's keep walking. No change, no change, no change. Bam! Now what? Take a step, go down 2. Take another step, 2 more. Take another step, 2 more, right? It's linear slope down. Remember the order of the lines. Okay? There, slope, parabolic. This is parabolic. And then, okay, what is that? Look here. If you have a downward force, boop, the next graph is going to have a flat part. If you have a flat, like that, a constant distributed load, the next graph down is going to have that. Guess what? The next graph down is going to have that, because this is the integral of that one. This is the integral of that one. Okay? Remember that? This is way back statics review, isn't it? So here I am at 6.94. I'm going to go down a total of 4. So that's going to take me to negative 10.94. Okay? Uh-oh, we didn't wind up at 0. Oh, wait a second. Look here. A John Denver force right there. Do you see it? Take me home to the place I belong on my shear graph. Back to 0. Everybody. Okay. All right, here we go. That's goofy. All right, here we go. I'm going to put little pluses and little minuses here. Okay, why do I do that? Remember? Because that tells me the slope of my next graph down here. So this next graph is going to go uphill, downhill, downhill. So it's going to go whoop, derp, derp. Right? That's what it should do. Let's see if we can plot it. Now, can we use the graphic method? Yes, we can. So this section here, how big is the area? 4.5 times 7.06. Okay. 4.5 times 7.06 equals 31.77. Okay, I'm gonna put a little circle around that, because that's the area of that shape, right? This little guy right there is 6.94 times what? 2, 13.88. Put a little circle around him. And then the last one is, what is this guy here? Well, remember, this is like a rectangle and a triangle together. Okay, so the rectangle is 2 times 6.94. That's 13.88. Okay, plus the triangle, which is 1/2. The base is 2. The height is, how big is that right there? You remember how much it went down? 4. Yep. The 2's canceled with the half, right? So 4 plus 13.88. Anyone? Anyone? Bueller, 1788. Okay. We're ready to plot. Let's go. Okay. Here we go. We're going to start off at 0. When's the only time you don't start off at 0? When you have a concentrated moment over here. But we got a hinge there. We're going to be at 0, yo. We're going to go uphill 31.77. Remember, this is straight across. So the next graph down is going to be slope, straight linear slope. Whoop. So here we are at 31.77. Now I'm going to go downhill 13.88. So 13.88, I'm at 31.77. 31.77 minus, that was still in my calculator, answer 17.89. So now, whoop, we are at 17.89. Oh, baby. Look how much we got to go down. Now, should you fret that says 17.88 and that says 17.89? Did we have a little rounding along the way? Okay. Yes, if you want to carry an extra decimal, you're going to get closer to 0. I know this has to go back to 0. I'm going to call that 0, okay? And how do I get there? How do I get there? Oh, that's the question, isn't it? Because look, this is at a slope, right? That's this guy. So I know I'm here. I'm parabolic. So here's my choices. That's parabolic. That's parabolic. Which one is it? Is it slow then fast, bunny slope then black diamond, or is it fast then slow, black diamond then bunny slope, right? Well, look here. How do we accumulate and load? Short stacks, fat stacks, okay? So this guy is slow then fast. So slow then fast, that's that top line, isn't it? This is fast and slow. It's not that guy, okay? That's probably the number one mistake I see on parabolic curves with students. It's just inverting that curve, okay? And that takes us right back to zero again. So there's our moment diagram. Here is our shear diagram. Y'all, that's statics review, isn't it? That should not be that bad, okay? So let's go back over there. We know I, we know C for our equation up here, right? What is M? What is the worst bending moment on that whole beam? You know what? It occurs right there. And it's 31.77 foot kips, okay? So over here, M, 31.77 foot kips. So, you know what? All we need to do a little calculating up here, don't we? Let's do it. Let's do it. Okay. Doesn't erase very good, does it? One day when I get rich, I'll buy y'all a new board, okay? So here we go. Sigma max equals M, 31.77 foot kips. Do we want feet? No, we got to have inches. I know if you had millimeters, you could just divide by that. Okay, I know. Okay, so what is a foot? I've got foot there, so I want foot on the bottom. So 1 foot is 12 inches. You know what? Bam. Now the feet are, it's gone. Now we're in inches. It's all good. So it's M times C. What is C? 3 inches. Divided by I, which is 54 inches cubed. And what are we going to be left with? I'm going to get rid of inches there. Okay. And I'm going to get... Okay. Now I'm going to give you a little secret, okay? I messed up. But there's a lesson here, okay? I messed up. How do I know I messed up? Look here. I've got inches here and inches there. That's 2, right? So that would have made that, what? Just inches. I would have wound up with kips over inches. That's not a unit of stress. It needs to be KSI, kips per square inch. Where did I mess up? It's pretty simple, right? Remember this? It's not inches cubed, is it? It's inches to the 4th. Come on now. Boy, I'm getting rusty, huh? So now 2 of the inches goes away, right? And now it's in KSI. We were doing right, but I'm telling you, the most important thing is, I've told you this 1,000 times on this channel, use your units on these, okay? Here we go, gang. 31.77, whoa, clear, holy moly, 31.77 times 12 times 3 equals 1143 divided by 54 gives you sigma max, and that's absolute max, okay, is equal to 21.18 KSI, kips per square inch. All right, there you go. We learned this way back in statics. Now it's coming in handy. All right, I hope this helps, and I'll see you next time here back on the channel.